stress X is equal to minus mz over izz multiplied by y. Okay, so I just put some x's into it. Right. By looking at the formula over here, and some of you say, Eugene, what is the y? Okay, so the y is this distance over here. Okay, measure from the centroid. This is the y. Okay, everyone measure from the centroid. This is the y, and measure from the centroid. This is the y. Now, I'm going to ask all of you a question. With these three cross section, okay, which one is classified as symmetrical bending? You can type on the chat to tell me which one is symmetrical bending. Anyone? Is it number 1 symmetrical, or is it number 2, or is it number 3? Before you answer, I want you to look at the formula, okay, where we calculate stress X is equal to minus mz divided. So mz is moment about z divided by izz, which is the second moment of area about the z-axis, multiplied by y. So by looking at that formula, which one is symmetrical bending? Anyone, please? Only number 1. Anyone else? If those of you support May, you can put your thumbs up. Anyone else? Only number 1. How about number 2? How about number 3? Number 1 is good. Okay. You are right and you are wrong. All of them are classified classified as symmetrical, as centric symmetrical bending. Why? Okay, why all of them? Okay, one more trap. It's not a trap, okay? It's not a trap because it's knowledge. You don't know how is it classified yet, okay? It's not necessarily a trap lead, okay? So all of them are classified as symmetrical bending. Why? Whether the structure is symmetrical or not, or whether the structure is under symmetrical or unsymmetrical bending is based on the stress field distribution. Okay, is based on your stress field, not based on the force, not based on the longitudinal dimension, but on the stress field. Why do I say that? Okay, if you look at number 1, stress X, okay, at point alpha is equal to minus mz over izz multiplied by what? Y. Okay, so I'm going to call this y1. Okay, y1. And if you look at stress X at point B or point beta is also equal to minus mz over izz multiplied by what? Y1. Right? So therefore, stress X at point alpha is equal to stress X at point beta. For all of them, right, if I call this 1, alpha and beta use the same formula. Okay, so stress alpha is equal to stress beta for shape number 1. For shape number 2, alpha and beta also have the same y1. And for number 3, alpha and beta stresses are also based on y1. Because mz over izz, remember mz over izz over here, regardless of alpha, beta, I or z, these are all what? Constant. Okay. And then if you look at I and j, I and j, if you look at I and j, so this is our distance, this is y2, right? If you look at y2, what we say that stress x at point I is equal to minus mz over izz multiplied by y2. And if you look at stress x at point J, is also equal to minus mz over izz multiplied by what? Y2. So therefore, stress x at point I is equal to stress at point J. Again, mz over izz is a what? It's a constant. Okay. So that is why we classify it as symmetrical bending. Okay, and more important thing is this. Okay, in symmetrical bending, or in centric symmetrical bending, the moment must only be based on one axis only. Okay, so what do I mean by that? If I were to sketch a 3D feature, now if I were to sketch a 3D feature, yeah, a very bad sketch. If I were to sketch a 3D feature, okay, if we were to sketch a 3D feature over here, right? And then on this 3D feature, this is our x direction. This will be our y direction. This will be our z direction. Okay. So if we have, so based on centric bending, stress x will be equal to minus mz over izz multiplied by y. Okay, so moment about z is this direction. I'll change the color. I'll change the color. So this is our moment about z using the right hand rule. Okay, another possibility, okay, under centric. Now these formulas are for centric symmetrical bending. Okay, the other formula is mx is equal to minus my over iyy multiplied by z. Okay, so for moment about y, what do I mean by moment about y? This is our moment about y. Okay, so in centric symmetrical bending, okay, you can only use equation A or you only can use equation B. So i.e. bending is only about what? One axis. Okay, so sorry, moment can only be applied about one axis. It's either based on mz or my. Okay. Now, the next thing I want to do is I want to elaborate on this formula over here. I'm going to elaborate on formula number 1, where stress, by right there's a minus sign down here, which I'm going to put minus, okay, let me put this properly, which is equal to minus my over I. Now, why the minus sign? So what I'm trying to teach you down here is, if you forget about the sign, it is okay. But before I go there, I'm going to explain equation number 1 and how equation number 1 should be used, okay? If you remember the full form of the formula, okay, which is stress is equal to minus my over I, okay? So now, let's look at the deformation pattern. Okay, let's look at the deformation pattern. Okay. So now we're gonna have a beam. Okay. So we're gonna have a beam that is originally. So let's get this out of the way. So this is X, Y. This is rotation about Z. Okay. And this is our beam. And this is our beam over here. Okay. So and then we have a load EY, and then we have this distance L2. Okay. So doing deformation, this is how, and then I'm going to call this is our point A. This is our point B, and this is our point C. Okay. So we are going to focus on calculating our stresses. Okay, we will calculate our stresses at point C only. Okay, we are going to determine our stresses at point C only. Can anyone tell me why do we focus at point C only? We are not interested at point A and point B. Anyone, please? Why do we focus on point C? Why don't we focus our stress analysis at point A and point B? Anyone?
C has the most deflection.
Yeah. So what? You are right. C has the most deflection. So what? Right? So what if it has the most deflection?
It would be the first place to crack or like
Yeah.
break.
So yeah, absolutely right. So at point C is where failure will what? Occur. So in stress analysis, we always want to know at what region failure will occur. Okay. And we pick point C for that reason because the deflection is the maximum. But if you don't know the deflection or maximum, then where are you going to calculate? Anyone? Let's say you don't know where. What are you going to do? So it happened to be, this is a very simple example. Okay, you just take your ruler. Hopefully your ruler has homogeneous property and you bend it. And where it's going to fail, it's going to fail at the center. Okay, so sometimes you can do cheap experiment like this. Okay. Okay. So when this structure deform, okay, when this structure deform, the structure will deform this